All right, so just to start things out, I'm going to be handing back your exams on Thursday. The reason I'm doing so is because I want to give everybody some detailed feedback on their resume. I looked over them enough to be able to give you a sufficient grade, but I want to be able to give you kind of feedback on how phrasing things a little better, so that way you can kind of take that feedback for the second exam and then for the third exam. Also, I think it would be good for you to want to have feedback. I think there's a career fair coming up next week, something like that. So having you had to prepare a resume and then have feedback on it should be helpful for you to try to maybe add some sort of summer internship or job that can help you offset some of your college payments. The exam scores were really good. The median was an 87, which is pretty good. The in-class portion, the median was an 80. That was a very challenging exam, and you all by and large rose to the challenge. And so that 7-point bump that came from the take-home portion, I called that on average. I called that a reward for willingness to be challenged. I know overall that was a challenging exam, and I imagine it took a lot of work. So your grade reflects your level of effort that I recognized from it. Does anybody have any questions about what we covered you've probably, other than going over it, you've probably forgotten quite a bit. We went over really briefly here, kind of some converting from MIPS to C. We get to basic addition instructions. Can somebody tell me why we had to break this down into 2 instructions? Right, exactly right, because we only have 2 registers that we can add and then put into a third instruction. Right, so we had to put in a temporary register like so. And so then this required you to kind of understand how to go through the MIPS encoding and actually see what's going on the MIPS screen sheet, so you understand how the architecture is actually working. So the same thing, this is order of operations. I briefly went over some common student mistakes. Another one, order of operations problem. Then I kind of started talking about pointers. And I'm going to be, when we go over pointers today in next lecture, I'll be hammering on this point over and over again about what a pointer actually is physically and how that'll help you improve performance or be able to actually do function calls. So we went over this a little bit here, and this is where we're going to start today's lecture. So so we have a branch, right? So we talked about branches as the result of this if statement or while statement. You're making some kind of decision, and based on that, you're telling it to go past either the branch or the loop at a certain number of instructions. So the MIPS data path has 3 types of instructions that are used for branches, and these are all immediate type instructions. So the first one is branch equal, branch if equal. If the 2 register values compared are equal, branch the number of instructions. Branch not equal is just the opposite. If they're not equal, branch. And then set less than is a value that we use where if one value is less than the other, then it's going to be 1. Otherwise, it will be 0. I think we briefly talked about this in previous lectures. So the whole idea is we don't have branch. MIPS does not have branch greater or equal, but does not have less than or equal. You get it to the point where often you have to do 2 instructions because it's a reduced instruction set computer. And the TGO down here, I do have all 4 combinations for A greater than equal to B, A greater than B, A less than B, less than or equal to B. So I'll be able to show you really quickly how the compiler breaks those down. Additionally, there are 3 types of jump instructions. So the jump, INSTR, this is the 26 bits value here that jumps to the indicated instruction. We kind of went over this briefly in the pseudo direct addressing where you have 26 bits, right? And then you shift left by 2, and then you concatenate the first most significant bits of the program counter. That means we're actually able to pseudo convey what the indicated instruction actually is, right? Jump register, this is actually an R-type instruction where we go to a register value and we jump directly there. This is going to be, you're going to find this at the end of pretty much any function call. So I take it you all have written some sort of function at this point in your academic career. And so you know that you have a main function and you call a function and it jumps to where, and we'll go over this, in the instruction memory, you're going to have some numerical value. Then you're going to execute those instructions. And then you have to jump back to the instruction after the function call, right? So you have the instruction before the function call, you have the actual function call itself, and then you have the instruction afterwards, which is why here we're going to see RA plus 8. So this is called jump and link, JAL. In case you couldn't tell if it's JAL or JAI. Jumps to the indicated address. It copies the program counter register to RA. So we have the program counter, and then we add 8, right? So we have the instruction, the program counter, PC plus 4 would just be the next instruction, right? So that would be the instruction where we have to jump down here to do the actual function call, right? And then we have to jump to the instruction after this one, which is why we have PC plus 8. So those are the 3 different types of jump instructions. We'll see how those are all used. So does anybody have any questions about it other than in my own lecture notes I asked what exactly are branching and jumping? Program, jump to the program statement at sublabel. All right, so this is just some notation indicating that you have your program counter, right? And it's going to be, and it's executing, it gets some sort of jump and link instruction, right? So then what's going to happen is you have the address, right? So you're adding the program counter to the register. But then here you have the address that you need. You're going to have some sort of, okay, so I have a better way of answering this question. So you have jump and link, and you're going to put the register address where you're going to put the program counter. The next instruction is going to be a jump instruction to tell you specifically, let's say 256, right? What that means is you're going to go down to the address indicated by 256 to continue the function call. And then after you complete the function call, you're going to jump back here. So this is PC plus 4, PC plus 8. Correct. So jump. Okay. So think of jump and link as two. This is a very good question. So think of jump and link as kind of like reserving your seat. You know, like when you're a kid and you went over to your friend's house, and you got seats, or you did whatever, however you called it. So jump and link is kind of just saying, hey, I got to come back here, right? But first I need to know where I'm going. So first thing's going to happen is I'm going to save my current location here, and then I'm going to go to Bailey, and I'm going to ask Bailey where I need to go. And she says, your function's call is back from Trentarius over here. So I'm going to go back here with Trentarius. We're going to work on our function, right? And then Trentarius is like, all right, we need to go back to Caleb. So the way this is working is when I do the jump and link, I have my original value, that's PC. The sublabel is Trentarius in this case, right? PC plus 4 is telling me where I need to go to do the function, and PC plus 8 is where I'm going to pick up after the function call. Does that make sense? Alex, did that answer your question? Okay. All right, so the next question that I have here is, what exactly are branching and jumping? So here, we actually have a little while loop. And it's while I equals j. So branching means that I do not want to do this code. When you've been writing code, you write code indicating that you want to do the loop, right? So while I equals j indicates that I do want to do I equals a of j and j plus plus, right? So when you're writing the code in assembly to indicate at the physical level what you're going to do, you're actually going to be doing the opposite of what's written in the code. The branch is going to indicate, otherwise you would just keep going. If you're not branching, you're just doing this instruction and this instruction. So in this case, you would actually be doing branch not equal, and we'll call S0I, we'll call S1J, and then we'll have some sort of sign extended value indicating how many instructions we're going to go past. So since it's an immediate value, we don't have to do the, we don't need to do a shift left by 2. We can actually have the compiler do it for us. So in this case, we're branching past 2 instructions, right? So we get PC plus 4. So let's say this instruction was 80, right? And so this instruction is going to be 84, 88, and 92. So I need to get to 92 if I'm branching, right? So here's the way you do the calculation. And this is we're going to be learning about this in section 5. So every time the program counter is accessed, the first thing you're going to do is increment it by 4. Right? Remember that PC plus 4 in the addressing? So your program counter is automatically going to come out, and then you're going to have an adder physically in the data path with a 4 on the input, and so you're going to have 84 here, right? So what the data path is going to do with this instruction is take the value from the immediate value, which is what we're trying to calculate here, right? And add this to get the value. So our end goal is 92, right? That's where we need to get to. So this ends up becoming plus 8, right? So what the value is actually going to, what you're actually going to see in an instruction, let me erase all of this for you, is 8. Even though I'm trying to get 12, right? So forgive me if I move over to section 5 really quick. The very first portion of the data path is the program counter, and it goes to the access memory address to go on the output, and then it's automatically incremented by 4 to do a bunch of other stuff. But that's in section 5, which we'll get to later. But that's kind of the idea. So the way you do it is if you know the original number, right, 80, and you know that you need to jump a branch past 2 to get to 3 instructions further, right? You only add, it's going to be, the way I would do it is you do 92 minus 80 minus 4. So you have the initial address, you have the final address, and then you take away 4 because you increment every time. For now, just press the I believe button. This is, I'm not throwing too much of it. So right now, it's going to come out to 8. So as I say here, branch not equal. We want to branch not equal. The reason why we want to do the opposite of what's going on in here is we want to indicate that we're not executing the code. If we do the branch comparison, S0 and S1 and 8, and it turns out that they're equal, that means it's not going to branch, and we're just going to go to the next instruction. Which in that case, we'll do the I equals A of J. And so here I have the opcode for its 9 hex, and then we have a intermediate value. I have 2 instructions here. I have a sample branch not equal. I don't know why it did that. So in this case, what ends up happening is we break it down. We're trying to access our code in here, right? So we end up having to branch a few more instructions because every time at the assembly level, we have to first, because we had I equals A of J, right? That was our first line of code. So what that means is we have to Remember, we have to shift left logical to get the value of j, multiply it by 4, which we have the shift left type 2, put it in a temporary register. Then we add the base address of the array S0, the offset T of 0, and I have some diagrams when we get into this in more detail, which will actually show physically what's going on. Actually, let me, if you don't mind, and I know 4.6 is there, bear with me for a second. Let me go over these diagrams that I drew up today. So you see this? All right, so this is what a pointer actually is, right? So, and it's the same thing as load word and store word. So in the event of a load word, like we're doing our shift left logical and then we're doing a load word, we're getting a value from data memory and we're storing in a register. So we're getting the value from the register, which is the base pointer of the array, right? And we calculate our offset. So in this case, this example here, I have 16. We go to the arithmetic logic unit, and the value of the pointer goes directly to, in this case, vals of 4, which is get vals of 4, which is what I have stated in the diagram. The base pointer of the array A0, which is this value here, is pointing to the initial value of the array. Then what happens is, now that I've calculated my pointer, I actually obtain the actual value of vals of 4 from the data memory, and then we come back, and then we store it in register T0. So there's a difference between the value of a pointer, which is the load word, and the value and the actual value. Here. Does that make sense? And then store word, the same thing, you're actually calculating. Okay, so that's, let me scroll down one more. So store word pointer. So basically what this means is now you're calculating your value. You have the value of the pointer, A0, which was the base pointer of the array, which we typically use in a function. We get this value here, and what we're actually doing in a store word is we're taking the value from the register, value of vals 4, and storing it there. So that's what load word and store word actually looks like. So to go back to where we were before 4.6, all right, so this is our actual code. So we are, in order to get A of j, we take S of 3, which is j, we multiply by 4, which is shift left logical of 2. We add the base pointer of the array to get that offset, so like we were trying to get the actual value. And then here, see, we put the value of that pointer is in T0. So then what's happening is we're going to load T0. In this case, I took a little bit of a shortcut, which is acceptable. I loaded it into S1 because I is equal to A of j, right? And I is S1. So instead of having to do anything else, I just loaded it straight into the variable because that was what it allowed me to do here. So then I just did an add immediate. The j++ is here, where we add S2, S2, and 1, or S2 and 1 and put it into S2. And then here, since it's a while loop, the other thing I do is I jump 64 to go back to the while loop because I have to do it again before I can break the condition, right? So in this case, we had 1, 2, 3, 4, 5, and 6. So to branch there, I know I need to get to 70, right? I need to get to 64 minus 1 and multiply that all by 4 because we're in byte addressing. So that becomes 5 times 4, which is 20, which is why this value is 20. Did you have a question? Huh? So these will become very useful, especially when you're studying for an exam, because I will have you do a C to MIPS problem on the exam, and it'll be similar to the one that I present later on in this section. So these are the 4 cases for I is less than j, I is less than or equal to j, I is greater than j or I is greater than or equal to j. So if you look at your MIPS screen sheet, you will see that what is known as BG or E or B L of E, branch greater than or equal to or branch less than or equal to, are what are known as pseudo instructions. They're not real. So what you have to do is you actually have to do, typically it takes 2 steps to convey all these. So if I is less than j, you can't do branch greater than or branch not equal, right? So what you have to do is you have to set t0 in the value, in this case, that you're setting the value equal to 1, or the register equal to 1, if S1 is less than S2. So in this case, what we're doing is we're doing a test. If I is less than j, then we're putting it in T0, right? That means it's 1 if I is less than j. If I is less than j, that means we want to do the code. That means we want to branch. That means we don't want to branch, right? So in this case, if T of 0 comes out to 1, we use our value $0. Remember, we have that initial register allocated for the number 0. This becomes very useful in calculating these results. So in this case, if I is not less than j, T of 0 will be 0. They will be equal, and we will branch the number of instructions. And if you look on your MIPS screen sheet, the notation that they use is PC plus 4 plus branch address, which if you remember from the previous problem, I had calculated out as, was it 70 minus 64 minus 1 times 4, which came out to 5, right? So this minus 1 here is being accounted for in this PC plus 4. If I is less than or equal to j, we set less than temporary register T0. I switch them around. S2, if j is less than I set T is equal to 0, and I branch if equal if they are equal. Because if j is less than I, that means I is not less than or equal to j, and then we can branch. Similarly, if I is greater than j, then what we can do is we can do a set less than if j is less than I, and then branch not equal, and you can probably figure out that it's branch not equal backwards for the other I is greater than or equal to j. So you see the pattern? In these cases, what we do is we take advantage of the set less than value, where if the first variable is less than the second variable, we set it equal to 1. And if it's not, we set it equal to 0. And then we base our knowledge of that on what we want to do for the branch, since we don't have branch greater than or equal to, or branch less than or equal to. Now, if you remember the comparator TGO that I had you do in the arithmetic section, and remember that it had greater than, less than, or equal to. And remember how the greater than had a significantly larger amount of gates that you had to add on. You remember that? Yeah. So if you have a greater than or less than circuit, you tend up adding a lot of area. So what the MIPS designers did was they took greater than or equal to or less than or equal to out of the MIPS data path, because the trade-off in area was not good considering the improvement of the 1 clock cycle of performance. So does anybody have any questions about this? The reason I included this TGO is because this is the most common mistake on any of my exams, and once I started including it, that mistake by and large went away. So hopefully this helps you out. All right, so I'm going to scroll past the first two here. So I kind of allude to these other two variable sets, or we had, register sets. We had B0 and B1. So we have two registers that are reserved specifically for return variables. The type of question you will see on exam will have some sort of while loop decision. It'll have some sort of if statement to test your knowledge of 4.6. It'll have some sort of integer pointer and some sort of array that you have to do some load and store values on. And then you have to demonstrate that you know how to do a jump. And then you have to demonstrate that you can return the value. And so the inputs to a function are in A0 and A3. So when I call a function, you'll see, when I write the problem, in the problem example you'll see on, when we get down to the end of this section, you'll have A0, A1, A2, and A3, where we have either pointers, what we're going to call pass by reference or pass by value. And then from there, you'll be able to make decisions about, presuming you're the compiler driving the micro engine, that you'll be able to actually execute the code. And you'll have enough of an understanding of C to be able to do the cadence courses at the end of the semester. So, what is C? Okay, so I've been alluding to lots of this programming language of C. The two people on the left here are Ken Thompson and Dennis Ritchie. So hold on, before you all write down 4.7, I put 4.7, we're going to write down fast. There's a reason I've included this as a TGO and as a probable exam question. I don't want you to just try to code in the language. I want you to understand why it is I'm teaching it to you, and why I think as electrical engineers, computer engineers, and computer scientists, understanding what C is doing will help you be able to code intelligently to an advanced digital system. So there was a B programming language before 1970 that no one codes in anymore because we have C. And so for basic combined programming language, and it was typeless. So you have int and array and well, not array, but in array or char, and basically everything they were trying to make it typeless and take advantage of arithmetic operations in the ALU, and then convey that as information. And oftentimes that takes a lot less memory. But we want to be able to add types. So this is where their invention of C comes in. Ritchie and Thompson invented C in 1970 by modifying the typeless B programming language by adding data types. So everything that you've been kind of working with and coding and taking for granted, that was not necessarily there before. By adding data types for variables and converting the compiler to produce machine code. Since C compiles directly to machine code, the compiler may derive code that allows significantly higher throughput. So they modified the B programming language to provide, and I'm going to scroll up here a little bit so those of you in the back can see this again. Ritchie and Thompson, who are these gentlemen here, every computer you've ever dealt with has had a contribution from these two, by the way. And Thompson invented C in 1970 by modifying the typeless B programming language by adding data types for variables and converting the compiler to produce machine code. Since C compiles directly to machine code, the compiler may derive code that allows significantly higher throughput. So the whole goal is running the computer fast. And MIPS, the whole goal is running the computer fast. High performance execution of compiled code. So I had the opportunity not too long ago to hear Ken Thompson, this guy, Dennis Ritchie, speak. How many of you in here have coded in C++? How many of you enjoyed that experience? Yeah, all of your hands went down, right? But there are professionals who have been doing it for 20 years who do not enjoy coding in C++. Basically, what they tried doing in C++, as you can figure, is they're trying to increment the C programming language by adding a ton of libraries. Well, the people whose job it was to take care of this basically allowed everybody in, right? And think about if you're throwing a party, you don't want to allow everybody in, right? There's some people, it's like, no, you're just going to cause problems, right? Don't invite the people that shot Harambe. Yes, I heard that. Right, but we all know that one person, like, yeah, all you're going to do is cause trouble. So same thing, C++, they kept throwing stuff in. It has a lot of good libraries, but it also has a lot of problems. And when somebody, so I had the opportunity to attend the Turing Awards in 2012, and Ken Thompson was there, and somebody asked him, like, what would Alan Turing, you all know who Alan Turing is, right? Okay, good. We're going to have to shut down lecture for a minute there. Somebody asked Alan, what would Alan Turing think of modern computing? And Dennis Ritchie said, if Alan Turing saw the C++ programming language, it would be like the inventor of the TV coming back and seeing the Maury Povich show. That to update that would be like if they saw the Keeping Up with the Kardashians. Yeah. So for those of you who had dealt with C++ and thought it was a miserable experience, you are not alone. That was not just you. It's pretty much everybody who's ever had to code. I had to write my dissertation work in C++, and I was ready to rip my hair out. So the growing popularity of C, people are trying to modify C, make it work for their own data path, and so they had to come up with a standardized C code. So that became the American National Standards Institute, established an unambiguous and machine-independent definition of the C language known as ANSI-C. So that's 4.8 is this one. So why do you think it would be important to make it unambiguous and machine-independent? Yeah, here, people mumbling around. And so that's understanding the difference between architecture and organization, right? So you're able to use the architecture and say, computer software people code in C, code it to the machine-independent set, and then we will design our hardware to be able to design the advanced digital system so we can execute it properly. We want to have high throughput, compile it down, and run it quickly. So C permits memory access to the computer and microprocessors. So this is something that's important for those of you who are, when you're if or when you are struggling with C in this class, here's a good motivator. 9 billion microprocessors were manufactured in 2005. 8.8 billion of them were embedded into products using C or assembly. And that is still consistent today. So that the skills that you are picking up on in this course, you will use again. And I have a quote here from industry professional. It's an important foundational language that requires you to understand the full stack of technology. If you learn C, you'll understand computers at a much more profound level than if you do not. So yes, as I know I'm throwing this code at you, I remember last lecture, your eyes started getting really big and looks horrifying, and I understand. It can be. I'll get to your question in a second, Bridget. But my goal is, this is something that I think is very, very important, and I modified the course to incorporate understanding of C. Yes, Bridget.
Okay. First, can you zoom out just a little bit so we can see the whole thing? And then the other thing, where does TG or 4.8 end in?
There's this one here. It's just that line.
Oh, just that line.
Yeah. So the other thing I consider, there's two more concepts here. Procedural programming versus object-oriented programming. So C++ is an object-oriented language, and C is what's known as a procedural language. So C is procedural programming uses a list of instructions to tell the computer what to do step by step, right? So you compile it down, you do what we're going to be doing in the problems, you have some sort of loop, you have some set of objects that you're using to represent your system, not objects, variables, types, integers, arrays, lists, and using those to you compile it down. In MIPS, we have the MIPS assembly language. So you have to understand the transfer language, how everything goes in between registers. And from there, you execute it step by step from the instruction memory. So that's what's known as procedural programming. So object-oriented programming, which you're familiar in C++ and we're very familiar with in Java, right? So you're able to create objects in Eclipse and be able to call objects and be able to do that. Object-oriented programming is an approach to programming where all computations are carried out using objects. So everything in Java is, start out with public static void main, and then you have an object where you're even calling an object system.out.println to do printing functions, whereas in C and C++ you would use fprintf, right? So there you're using instructions, whereas in object-oriented you're using objects. The other thing that's important to understand now, I'll say it's possible. I got to figure that out if I have the time on an exam to ask it. But 4.10 is also pretty important. So there's 3 types of modeling that go on. So we're going to learn C, and later on you're going to learn System C. You're going to learn VHDL and Verilog, and then if you take low power VLSI design or CMOS VLSI design, you will learn about this thing called geometric modeling. So the first one is called behavioral modeling. Behavioral modeling is an explicit definition of the mathematical relationship between the input and output with no implementation information. So you're not worried about what the adder really is. You're just writing C equals A plus B, right? You have some inputs. You have 2 variables. Then the computer does something magical because it's transparent to the programmer, and then returns some sort of result. Part is structural models. This is where your VHDL and Verilog is going to be learning later. How can you actually write code that simulates hardware itself? And you can actually test it and use it to synthesize the hardware, whether it's on a board, like you'll do in 3D6, or being able to simulate having it run through a Tensilica processor, like you'll do later in this course. Structural modeling is the implicit definition of input-output relationship through a particular structure using interconnection of computers. So in VHDL, for example, the actual architectures are, you have a 1-bit adder, and then you would have a full bit adder, and then you could use XOR as the inputs to build your input-output adders. Or then you could actually design memory. You can actually design your data path. And you can see how that actually flows through. And then the third one is geometric modeling. Deals with how the system is laid out in physical space. How do you actually take transistors and design them to lay the actual metals, the silicon, on each other to allow the electrons to flow through them in order to produce logic? How can you represent ones and zeros? So that's done in geometric modeling. It's also known as physical modeling. Now, I'm going to zoom in here on 4.11. This is what's known as the Cocoon Chart. So I'm going to read through all of this. This is kind of where everything is in the behavioral, structural, and geometric spaces. Let me read through these definitions one more time for those of you who didn't get. So behavioral modeling is the explicit definition of a mathematical relationship between the input-output with no implementation information. So here, and I'll zoom in again so you all can see it. systems, algorithms, register transfer language, logic, A plus B or A XOR B. You don't know how the XOR is being done. It's just there's logic. And then transfer functions, which transfer function is just moving values from one to another. So like move. So we're not going to really go into move instruction, but 486 you'll definitely do this where you have EAX and then A1. So you're moving a value into a register. Here you can just do that by doing add your initial register, your final register, and 0. So the structural modeling, the implicit definition of the I/O relationship through a particular structure. So here, you're structuring, you can actually do the CPU and the memory, and then when you go down a level, you're actually doing the systems and buses, and then you can actually code the ALU. You actually did a little bit. So remember the TGO where you had all the inputs representing which binary values represented addition, subtraction, set less than, all that. That is an example of structural modeling. And the language I presented in was in VHDL. And then geometric modeling deals with how the system is laid out in the physical space. So if we zoom in here, behavioral there's no implicit understanding what's underneath, just the input and output. So any system, right? All right, how many of you are familiar with algorithms? We have other than, so I did present some algorithms for what we did for, sign multiplication, restoring and non-restoring division, right? So there was some sort of, you have to understand how the bit shifts occur, like shift left and shift right at certain points of the algorithm. But in general, you don't know the physical details underneath. So register transfer, that's what we do a lot with the MIPS assembly language, and then logic, and then transfer functions. And this thing is 4.0. You will see this over and over and over again. You'll probably see this for you electrical engineers. You'll probably see some variant of this chart in pretty much every class that you take. It's a good idea to know it. So you can actually simulate CPU memory. You can simulate systems and buses. You actually wire, a wire, and then that you could actually connect, two adders. So if you had an adder one, you had A and B, C in, then sum and C out. You would actually create a wire here to go to the next adder. So that would be your C in for the next adder, right? So you would actually write code to simulate a bus or a wire. Then you can then all of this builds up to an arithmetic logic unit. Then you can write gates and flip-flops, how you allocate that into space, and then the transistors themselves. So in the geometric space, you have chips and partitions. So you have the whole computer chip, right? Remember that I showed you the Intel 4004, the first lecture? So then you have clusters and everything kind of, remember how everything in memory, you have temporal and spatial locality, how you can take advantage of that with proper design of memory at the physical level. Then floor plans. So we're not really going to go into what floor plans are in this course. That's something that's covered a lot in 482. But the general idea is how do you optimize how all of the silicon and the memory and the cache and the arithmetic logic unit and the control unit is laid out on a computer chip so you don't overuse one part of the chip. You don't want to just continuously burn one part of it. You want to try to spread that out as much as possible. And then cells, so say you have the whole floor plan, so then you have an arithmetic logic unit, you have your cache memory, you have your data memory, instruction memory. I'm just coming up with random sizes here. The controller and other devices. So all of these are cells, and inside the cells there are smaller and smaller cells to represent different aspects of the design. And then polygons ultimately boils down to, if I'm drawing out a transistor here, you have a P well, an N well, and then you have input A and output out. And this is kind of a very incredibly basic design of an inverter at the transistor level. So that's how all of this works for that. you can act, yes.
There's rings. Is there a significance to each ring?
No, there's not. It just they just had 5 in each one, so they thought it'd make it look pretty. You don't have to draw them. That's actually a good question. I actually think I asked that once upon a time, and I got the same answer. So moving on. So how do you write good code so it produces high-performance compiled code in the micro engine? Y'all familiar with XKCD? Yeah, so I included an XKCD comment, how to write good code, start project, do things right or do them fast. You can break it into right or fast, code well, yes or no, are you done yet? And it goes in an infinite loop, start it all over and throw it out. And then you have the rest of the flow chart. And then over here you magically have this good code. How do you write that? So let's take a look at a C function and see how it actually works in the underlying language. So here we have a function that I just call while function. And I have an input star vowels, int I, int star sum, and int j. So from what we can tell, vowels I is actually an array. Sum is actually an integer, so this is an integer, but it's a pointer to an integer. And so the way C works, and this will make a lot more sense when we go over those diagrams that I did again, because they're specifically drawn out to explain this concept of when do you, for those of you who've done C++, you probably got real confused at some point at some line of code like this where it's star sum plus equals vowels of I, right? So why do I have to do star sum, but I don't have to do vowels of I, even though when I call it, I have star vowels here and star sum there, right? That's something that gets a lot of students hung up, and so we're going to address that today. I'm going to explain it thoroughly by having an understanding of how the advanced digital system works. So I would say this may look very intimidating, but it turns out you have already learned everything you need to know to solve this problem. It's just a matter of now learning how to apply it. So a lot of this just has different combinations of shift left logical, load words and store words, being able to do branches, jumps, and then jump registers. So if you recall, remember this base addressing, right? So this is going to come back again. So load word and store word. So we have some sort of immediate sign extended to 32 bits. We get the value from RS, we decode it, we get it from the register itself, and then we calculate some, and if you recall from that lecture I just said, and then we get something magical from the data memory and just press the I believe button for now. So today is the day where I teach you what the I believe button was actually trying to say. So in order to understand this, we have to understand the difference between pass by value and pass by reference. So if you remember the register names, we had these values for passing a value back, and then we had the arguments to our function. So we can have up to 4 in this case. So be joyed that I cannot ask you for a function in the exam that goes above 4 registers. But you have to, but all of them are 32 bits, right? So everything has to be 32 bits regardless of whether it's a value or a reference. So we have to use the load and store operations to be able to tell the difference. So if you recall from this line of code, we have star sum, star vowels, and then we have these 2 other variables that don't have a pointer at all, right? So what's going to happen here is we're passing all of these values in those A0 through A3, right? So here, what we're doing is we have a combination of pass by value and pass by reference, which we'll define in a second. But what I'm doing is I'm actually passing the base pointer of the array of vowels. I'm passing the actual value of int I from the function. You all remember in functions where if you pass the value and you update it in the function, it doesn't actually update in the higher function? You're going to actually see why that is today, physically. Star sum, I actually have, it's still in data memory, but instead of an array, it's just one variable. And then in J is also being passed by value. So I'm jumping around, but basically it's just the same thing I'm saying here. I'll repeat myself. It's worth repeating myself. So A0 contains the base pointer to the array of vowels. A1 contains the numeric value of I. A2 contains a pointer to the address in data memory containing sum. And A3 contains the numeric value of J. So 4.12, we define pass by value and pass by reference. When we pass it by value, a copy of the value of the actual parameter is stored. So in main, the actual parameter is stored in S0 through S7, right? We then make a copy and put it into A1, which means anything we change in A1 has no impact on the value of S3, right? Which is why pass by value doesn't change the value in main, because they are actually two physically different copies of the variable. Now, passing by reference, if I want to do something in the function that I want to know how it's changed, and remember we only have two return variables, right? So I have to have other kind of ways. I can update the array or I can update the pointer. And I do that with pass by reference, which is a copy of the address of the actual parameter is stored. And as I've said before, A0 and A2, which were star sum and star vowels, were examples of pass by value, pass by reference, and A1 and A3, which were I and J, were examples of pass by value. So this next line was while vowels of I equals 0, right? So we've actually learned branching now. So now you can actually say what it is I want to do. So if they're equal, what does that mean what I want to do for my branch? What kind of branching do I want to do? If I'm seeing vowels I equals 0. Branch not equal. Very good. Very good. So what we have to do is we have to get the value of vowels I and then do a branch not equal and see how many instructions we need to branch. So first thing we do, remember we do the shift left logical, where we have A1. A1 in our problem statement is the value of I, right? So remember in the previous examples from last lecture, you have to actually calculate the value of I because we don't know until runtime. We multiply by 4, so we do the shift left logical by 2 because of byte addressing. We store a value in a temporary register, and then we know that the base address of vowels is stored in A0. So what's actually going on here is we're adding 0, the base address of vowels. We have the offset is T0, and that gives me the actual location of vowels I, right? It gives me the location, but I don't have the value yet. I have a point. I've now calculated another pointer. So then what I'm going to do is I'm going to load. I'm going to use this here. What's actually happened, if you remember that drawing, I took T0 and 0. We put them into an arithmetic logic unit. Then that points to the place in data memory where my information is. And then I load it from the data memory into the register. And so the question here that I get sometimes is, well, I have T0 here, right? And I'm adding it, and I'm putting it in T0 again. When we get into the data path design in the next section, you will see that once it comes out of the data path and you no longer need it anymore, you can immediately rewrite it in the same instruction. So that's another I believe button for the time being, but we'll get there. And then I always say wait for the sign extend value because we're going to calculate what it is. And then if I does not equal, or I is less than or equal to j, So we have if you recall from the previous TGO, we know that if it's, we have to set less than, I is equal to j, and then we branch equivalent. I have branch equivalent there, that doesn't make sense. This is a typo. But you all are probably copying 4.13 anyway. So if you recall from the previous topical guide objective, if we have I less than or equal to, that means if I is greater than j, that means we want to branch, right? So we'd say if j is less than I, we set less than. So we would do SLT, and we can say T0, A1, A3, and A1, right? So now we've met the condition. We set it equal to 1 if we meet that condition, and then we would do, if in that case, if j happens to be less than I, if I happens to be less than j, so if j happens to be less than I, that means we've met the branch condition, which then we do the branch if equal. So this should be T0 and 0. So now we're going to see in 4.13, we're now going to go over these diagrams in more detail. After addressing this, how do we know the difference between int star sum and int star vals when vals is an array and sum is a variable? In C, you must use the star sum in the code like we did here. Scroll. The reason we have to do that there is because we actually have to indicate that we need to load and store it in memory because it's a variable, whereas it's assumed by the compiler if it's an array. So in C, you must use star sum for a variable that is passed by reference in order to indicate that you must load the variable from the data memory and store it to the data memory after every loop. So if you ever had this, let's say instead of star sum equals b plus 1, right? Let's just say we did this. Sum equals b plus 1. What are we actually doing? We're taking the value of b. And so let's, I'm going to go to the next diagram here for a second. So we know that the pointer to sum is here, right? So if instead of doing star sum equals b plus 1, we just did sum equals b plus 1 in the function, right? Here's what's actually physically happening. Star sum of b plus 1 is taking the value, the base pointer of sum, calculating the address, and storing the value back in the register. And at that point, we then add b, right? b plus 1 to that value in the local copy. If you are doing sum of b plus 1, what you're actually doing is you're taking the A2, so you're taking b, right? Some sort of b, we'll just say it's T3, right? You're taking T3 and 1, you're adding them together, and instead of going to data memory, you're overwriting the copy of the address. So you're no longer pointing to sum, you are now pointing somewhere else. That's why you have to do star sum in the instance where you have an integer there. Does that make sense? Because you're actually overwriting the value in the registers, and you don't want to do that. You actually want to update the copy of the variable. So here, going through here again, so this is int vals load word pointers. So we get vals of 4. We have our A0, which is our base pointer of load word. We have our offset, since it's 4, we calculate 4 times 4 is 16. This is the value of the pointer, right? So that means we go to here. So the base pointer here was pointing to this value, vals of 0. By adding this 16 here, we have A of 0 and 16. And now we're pointing to the actual value we want, vals of 4. So then we actually get, it's pointing to the location, then we get the actual value of vals of 4. You see the difference between address and value? And then we load it back, and we store it in the T0, which is what we indicate here. Does that make sense? Does the load word physically what's going on there make sense? Especially for an array. So the next diagram is, I also made a big note here. So big endian, E-N-D-I-A-N. What that means is that I think I got this question, but there's an actual term for it. So remember we have 4 bytes, right? And if we do the most significant bit into the least significant bit of the 32-bit value, the most significant bit is going to be the first one we obtain. And that's called big endian, E-N-D-I-A-N. If it were the smallest, it would be little endian. And I was going over the Tensilica videos yesterday. I noticed that there was a term that they were using a lot. So I'll refer to it to help you all out. So star sum is different, right? So instead of actually getting a value from an array where we have a base pointer, we actually know the location in data memory of sum. And we do that load word, it's going to be 0. So we take an A2, it's a 0, we calculate the value, we go to data memory, and sum is actually there. Then we get the value of sum and put it back in the registers, right? So that's the difference between a pointer to an integer and a pointer to an array. For store word, what we're doing is we have vals of 4, so we calculate 4 times 4 is 16. We have A of 0. So now we're pointing again to our vals of 4. We have A of 0 here, which is our initial value. We have 16 was there. The actual value is stored from T0 to the data memory. We had to know the offset that we had to calculate here by this value. In int sum, we have A2, which is the location of sum. We have 0 again. We get the value we want to point to. And then from T1, we get the value of sum to store into the data memory. So that is how pointers physically work. Does anybody have any questions about that? All right. So I think this is the last. Okay. We're not going to do 4.7 and 4.8. I don't know why those were still. I thought I had deleted those. So 4.6 is this is the same bit of code that we've just gone over in detail. So I want to review it again, and this will be the end of section 4. Though we can look at the examples that I won't assign just to see if you guys can give you an opportunity to struggle a little bit with C code and see if you guys have any questions. Fair? So here's the way it'll be phrased on an exam. Translate the following C code into MIPS assembly language. So you'll have the MIPS screen sheet available to you, so you'll be able to reference it. Vals is an array of words allocated in main where I is in A1. The pointer to sum is in A2. J is in A3. And the base address of the array vals is in A0. And the return address is stored in RA. So we're adding one more concept here. We need to have the actual value that we're jumping back to. The address of the first instruction of the while loop is going to be 256. And return the value using V0, and the return address is in RA. So the function is this while function. We have int I, int sum, and int j. So we have a while loop. Well, while vals does not equal 0. If I is less than or equal to j, star sum plus equals vals of I, then vals of I is plus equal to j. So before you all write this all down, what are some of the concepts that I'm asking here? Think like the professor for a second. What do you think why do you think this is a good comprehensive type problem? What are some of the concepts that I'm getting at here that don't involve your phone? Harambe's alive, he's texting him. Getting your hopes up on purpose. What do you think? Pass by reference, pass by value. Branching. Good, this is exactly what I want to hear. Throw out some more. Pointers, very good. What else?
C code?
C code, very good. Others?
How to deal with inequalities and
Very good. How do we branch with inequalities, right? So another thing, how to deal with inequalities, branching. You guys talked about jumping. I have an immediate I++ here. So you have to know how the immediate values work. I have something where I have to load a pointer to an integer and load a pointer to an array. If you can complete this problem, you will understand everything that C can throw at you. Does that make sense? No. That's why I'm asking it this way. And then I have a return statement that I can test your understanding of how the actual registers work. This is a really good comprehensive type question. So we start at 256. First thing I want to do, I have to do this comparison here. So vowels of I does not equal 0. So I have to calculate the value of I. I shift left logical. I multiply it by 2. Multiply it by 4. This is shifting left by 2. So first instruction is SLL. And in this type, students sometimes will get a little more clever when with temporary registers. I used as many temporary registers as possible, specifically so you can trace how everything's going if you're having a concept issue. Ultimately, as long as you're reusing the temporary registers properly, I will give you full credit on an exam. So then I have the value of I. I need to add the offset to the base pointer of the array, which is stored in A0, right? So A0 plus this new value of T0, I'm storing T1, which is now pointing at vowels of I. It's pointing there, but I don't have the actual value. So 258, I'm load wording here. It's 0 because T1 is now pointing exactly where I want it. I don't need any more offset. And T2 now contains the value of vowels of I. And so now here we're branching equivalent. I've left the values blank here because last thing I want to do is have you guys go back through and calculate those values. Because vowels does not equal 0. So I want to branch if they're equal. If they are, that's where I want to get to this value, right? So it's branch equivalent T2, the register 0, and a value that we're going to calculate here in a minute. Next, I have this I is less than or equal to J, right? So we do not have BLE. It's a pseudo instruction, so I need to use my knowledge of those types of instructions here. So I'm going to set less than. In this case, it's going to be J. I have S2 and S1. This should be J is A1 and A3. Okay, so this should be A3 and A1. Okay, so basically we're setting T3 to 1 if J is less than I. That should be, if J is less than I. So here I wrote my pseudocode properly, but I screwed up the transition. So instead of S2 and S1, that should be A3 and A1. So that is a typo. And then from there, we have our second case. So we're going to branch equivalent if T3 is equal to 0. So if T3 is equal to 0, that means we have not met the condition. That means we want to branch. There's a very technical yell right there. It's like Dumb and Dumber. You want to hear the most annoying sound in the world? when your professor is. So here we have our comprehensive how do you understand pointers there question. So first thing we need to do is we need to actually load a value from sum. I'm sorry, I meant to say we already have our value of vals I loaded, right? We have vals I loaded in T2. So what I need to do is I'm going to load sum into T4. So I have A of 2 is the pointer to sum, is not the actual value of sum. It's a pointer to sum. Go to the pointer, grab me the value, put it in T4. And then what I can do is, since it's a plus equals, what I'm actually doing there is I'm adding T4, which is sum, T2, which is our current value of vals of I, and putting it into T4. Now it's a pointer. So what does this mean? Every time I update the value of the pointer, that means I have to update the copy in data memory. So the next thing I need to do is I need to do a store instruction, which is this guy, or this girl. I'm not going to discriminate. So now I have the value of T4. I'm going to store it to the value of A2. Right? So now I've updated star sum. Now I have this vals of I plus J, right? So now I have T2 and T2. I have A3. A3 is J. T2 is my current value of vals I. So I can just add them together into T2, right? So once again, I've updated a copy that's supposed to be in data memory of a local register. So in order to fix that, I have to update it in data memory. So therefore, I have the store word. So T2 is the updated value of vals I, right? T1 still happens to be, wherever I stored it here, the base pointer to vals of I, right? See, I still have it up here. I haven't updated it. So now I can just put that value back. Does that make sense to everybody? So now I put the value back. And then I have to, so now I'm at the end of this branch, right? So now I know the next instruction I need to be at. So this I++, which is add I here, is 267. So now I know the first thing I need to do here. So it's going to be 267 minus 261 minus 1 for that PC plus 4, right? And that's all going to be multiplied by 4. So that's going to be 7 minus 1, 6 minus 1 is 5 times 4 is 20. So this value is now, we can now go back, and if I use the ink color that's visible, we can say that's 20, right? Add I is just I++. So now I know that after the I++ is where the while branch is going to be. So here it's going to be, I want to jump to, so I add this jump 256 because this is the end of the while branch and allows me to go back up here to start the while loop again. And so I want to go to 269 for this one, minus 259 minus 1 times 4. So that's going to give you 9 times 4. So this will be 36. And then last but certainly not least, we have this function return I plus equals j, vals of I, right? So in this case, I still have vals of I in T of 1. I have not updated, so I'm able to do that. I am cognizant that we're of a minute to go. It's okay. We add them together, and I use V0 as my return register, so then I can actually return that value V of 0. And the last thing is we jump register to RA. That allows us to go back to the function that called it. So it's going to be the rest of section 4. This is where we're ending here. Work through this problem. Come with questions next lecture, okay?